My name is Jesse Cresswell, and I'm here to talk about the generation of calorimeter showers with density estimation on learned manifolds. Experiments at the LHC require simulations of how particles interact with its detectors, but doing these simulations with physics-based approaches is incredibly slow. So the Fast Calorimeter Simulation Challenge asks us to train a surrogate model that can generate realistic showers much more quickly than physics-based simulations. Of course, this is a great application of deep generative models, which can be trained on shower data to learn the distribution and sample much more quickly. And over the past few years, there's been a number of approaches in this vein. But I think it's worth taking a step back and reconsidering exactly what modeling assumptions we're using for this. Consider, for example, the manifold hypothesis from machine learning, which states that high-dimensional real-world data is supported on a low-dimensional manifold embedded in ambient data space. Well, when you look at electromagnetic calorimeter showers, you see they're highly structured. They come from processes in quantum electrodynamics, which is incredibly constraining. So this means that the target distribution which we're trying to model, P star, should be supported on a low-dimensional manifold M and not all of RD. But many deep generative models, such as normalizing flows, learn a density which has support over all of the ambient data space. So what exactly happens when we try to model a low-dimensional distribution with a model that has a high-dimensional density? Well, in this case, maximum likelihood estimation fails. A phenomenon known as manifold overfitting occurs, where the manifold will be learned, but not the distribution on it. So in this example on the left, we have a two-dimensional data space and a one-dimensional manifold inside it, on which there is some distribution defined. On the right, you can imagine trying to train a density model which has support on the full two-dimensional data space. Now, to maximize the likelihood of the data, all you need to do is send the density to infinity across the manifold in any configuration you like. It doesn't have to look anything like the distribution on the left. And you can do this while still having a normalized density function, because the density only needs to go to infinity on a set of measure 0, namely the manifold. So the simple solution to this problem is to take a two-step approach where we first learn the data manifold and then estimate the distribution on it. So in step 1, we train a generalized autoencoder, which is any model that constructs a low-dimensional encoding and then has a way of reconstructing the data from latents using a decoder. Then when we have that low-dimensional representation of our manifold, in step 2, we'll do density estimation on the manifold, for example, using maximum likelihood. And that gives us a low-dimensional density P of Z, which should reflect the true distribution of the data. As a proof of concept, we use this approach on a data set of photon showers. And that data set comes with a 368-dimensional representation of the data. To understand the intrinsic dimension of the data set, we used a statistical estimator, shown here on the slide, which can be applied directly on the data set. And it shows that the data has an intrinsic dimension of 20, not 368. So now we can apply our approach. In the first step, we train a VAE with a 20-dimensional latent space to learn a representation of our manifold. And then once we have that, we can train a normalizing flow on the 20-dimensional latent space to estimate the density. We can sample from the combined model and compare those samples to a test set to see how realistic the samples are and how accurate the distribution has been learned. So on the bottom, we have a few histograms comparing the distribution of generated samples to the test set on a number of high-level features that are motivated by the physics. We see that the agreement is quite good, especially for the very small scale of these models. To wrap up, I've talked about how calorimeter showers have low-dimensional structure and that we should be accounting for this structure with our modeling assumptions. We can do that by first learning the manifold and then estimating the density on it. And this gives us a more principled approach to maximum likelihood estimation, which avoids the problem of manifold overfitting. In addition, two-step models reduce the dimension of the data so that training and sampling is extremely fast compared to full-dimensional density models. So do come by our poster if you want to chat more. Thanks for listening.